The goal of this section is to find what are called inverse functions for a given function, or an inverse function for a given function, and that's basically the function that undoes what a given function does. Before we can talk about finding the inverse, we have to talk about a property called being a one-to-one function, because only what are called one-to-one functions have inverses. So that's where we'll start. We'll start with the definition of a one-to-one function. And the definition is this: a function is called one-to-one if any two different inputs in the domain correspond to two different outputs in the range. In other words, if x1 and x2 are different inputs of a function, f is one-to-one if f of x1 is different from f of x2. Let's say this another way. Every output corresponds to only one input. Or even another way, if given an output, we can determine uniquely its input. So, it's different from just being a function. For a function, every input has only one output. So given an input, we know its output. This is kind of the opposite. So given an output, we know its input, and there's only one input that goes with it. So let me sketch a one-to-one function. Here's an example of a one-to-one function. If I pick any output, let's say this y value, there's only one input that it came from, right? There's not another place where the y value is that particular value. So graphically, a one-to-one function passes what's called the horizontal line test. And that means each horizontal line crosses the graph at most once. Let me also sketch a graph that is not one-to-one. This graph is not one-to-one because I could draw a horizontal line that crosses the graph more than one time, in this case 3 times. Because there are multiple inputs corresponding to the same output. So if the graph fails the horizontal line test, it's not one-to-one. If you can find a horizontal line that crosses the graph more than once, it's not one-to-one. But if every horizontal line crosses the graph at most once, then the graph is a graph of a one-to-one function. So in example 1, we have a set of input-output pairs, and we want to figure out whether the function is, or let's say the relation is one-to-one, function or relation, because some of these are not functions. First, A here, we have 1 is paired with 2, 3 is paired with 4, 5 is paired with 6, and 6 is paired with 7. So our outputs are 2, 4, 6, and 7, and they each appear with only one input. So this is, yes, a one-to-one function. Each output is paired with only one input. The next one, 8 is paired with 6, 9 is paired with 6, 3 is paired with 4, and negative 4 is paired with 4. So we can see two problems. 6 is paired with two inputs, and 4 is paired with two inputs. So this is not a one-to-one function. The outputs 6 and 4 are each paired with multiple inputs. The reason we care about this is that eventually we want to do what's called reverse the function. So if someone gave me the output 6, I'd want to say, oh, that came from 8, rather than, oh, that came from 8 or 9. We want to go back to a single specific value rather than saying, well, I don't know which one I should go back to. Example C here, we have the input is a person in the class and the output is birthday month. So we want to know, for the set of outputs, are they each paired with only one input? That would only be possible if everyone in the class has a different birthday month. And since there are more than 12 people in the class, we know there's no way we can all have a different birthday month. So this would be not a one-to-one function. Some output, the birthday month, must be paired with more than one person. All right, so D is kind of a tricky one, or maybe even I could just call it a mistake on my part. This isn't even a function. So if it's not even a function, we can't talk about it being one-to-one. So this is not a function because inputs are paired with more than one output. This fails the vertical line test, which is our graphical test for functions. And then we have here, again, a statement of the horizontal line test that I had discussed and written above. But if every horizontal line intersects the graph of f in at most one point, then f is 1 to 1. So you can see the discussion up above again. Example 2 here, we want to think of a function that is decreasing on its entire domain, having its domain negative infinity to infinity. So an easy example would be just a linear function with negative slope. So we could say maybe f of x equals negative x plus 3, something like that. Any linear function with a negative slope would satisfy this requirement that we've got decreasing on the entire domain with domain negative infinity to infinity. Is the function 1 to 1? Certainly graphically we can see, yeah, it passes the horizontal line test. So yes, f is 1 to 1. It passes the horizontal line test. And then we want to generalize this idea. If we have a function, maybe we don't even have a formula for the function, but if the function is increasing or decreasing on its domain, the whole domain, so it never turns around, so the function graph never changes direction. It's always just going down, even if it just slightly. Maybe it goes down quickly for a while and then levels almost out and goes down more. Maybe even almost has a horizontal asymptote. If it's decreasing always or increasing always, the graph has to pass the horizontal line test. So it is a one-to-one function, or it must be. So any function that's always increasing or always decreasing will automatically be one-to-one, so it will automatically have what's called an inverse, and that's what we'll talk about soon here. One thing that will be new for this course that we didn't talk about in intermediate algebra is the idea that if we have a function that's not one-to-one, we can restrict its domain to create or force a one-to-one function so that we can talk about the inverse on a restricted domain. And this example is going to highlight that idea. So the function f of x equals x squared minus 3 is not one-to-one on its entire domain. You can think about the graph of that function. That's a parabola shifted down 3 units. So the graph looks like this. So just visually we can see, oh, that fails the horizontal line test, so it's not one-to-one. But we can try to find a restriction of the domain on which the function is one-to-one. So the problem comes when that function turns around, so at the vertex. So if we can include just one side of the vertex or the other as our x interval, then on that domain the function is one-to-one. So let's say our greatest or largest possible restricted domain would be either going from negative infinity to 0 for our x's, or from 0 to infinity. So either x less than or equal to 0 or x greater than or equal to 0. So splitting at the vertex and just including one side or the other. So in one case we would be thinking about like the left side of that graph. In the other case we would be thinking about the right side of the graph. Either way, the graph on that restricted domain is 1 to 1. I should say the function on that restricted domain is 1 to 1 because the graph passes the horizontal line test. And now we'll be able to talk about this idea of an inverse function. So here's the definition. It says, suppose that f is a one-to-one function. Then to each x in the domain of f, there is exactly one y in the range, because f is a function. And to each y in the range, there is exactly one x in the domain, because f is one-to-one. So we've got one x paired with one y paired with one x. The correspondence, or the relationship from the range of f back to the domain of f, is called the inverse function of f. So we just basically turn the outputs of f into the inputs of f inverse, and the inputs of f to the outputs of f inverse. The notation we use looks like f with an exponent of -1. This is not the same as the reciprocal. So we need to know from the context that we're talking about f inverse, not the reciprocal of f. They're different things. So like I said, informally, f inverse is the function that reverses the action of f. So the domain of f is the range of f inverse, and the range of f is the domain of f inverse. They just get reversed. Another way we can think of this as xy pair in f, then we have yx as a pair in f inverse. Instead of x's and y's, let's use a's and b's. I think that might be less confusing, because we're still going to call our inputs x, whether we're talking about f or f inverse. So if I have a coordinate pair AB in f, then I have the pair BA in f inverse. Another way to say it is if f of A equals B, then f inverse of B is A. Okay, so if I want to find the inverse of each of these functions, if this is the set of ordered pairs that defines the function f, then to talk about f inverse, I'm just going to switch them around. 2 would go back to 1, 4 would go back to 3, 6 would go back to 5, and 7 would go back to 6. So the inputs of f become the outputs of f inverse, the outputs of f become the inputs of f inverse. So we could say f of 5 is 6, but we could say f inverse of 6 is 5. That's a separate thing, but just finding the inverse of each function, that just means in this case list the ordered pairs like we did there. When we have a graph given instead, we can just switch the ordered pairs graphically. So if this line is f, that contains 1, 1, f inverse would also contain 1, 1. F happens to contain 2, 4, it looks like. So f inverse would contain 4, 2. Let's see if we can find one more. Here we've got 0, -2. So f inverse would contain -2, 0. And then we can just connect these lines. We can see that f actually had slope 3. It looks like f inverse has slope 1/3. So this would be the graph of f inverse. Since we're just switching the x and y coordinates on the graphs, one thing that's interesting is that the graphs of f and f inverse are always symmetric across the line y equals x. Again, that's just because we're switching the x and y coordinates. So if you fold that graph in half along the line y equals x, the two sides should match up. So the graph of f inverse is the reflection of the graph of f across the line y equals x. One more example here. C, we've got, looks like, let's just track the corners. That's 1, 1 again. So f inverse would have 1, 1. This is 0, negative 2. So f inverse would have negative 2, 0. And then it looks like we've got, what, 4, 3. So f inverse would have 3, 4. And it looks like we've got negative 3, negative 4. So f inverse would have negative 4, negative 3. So if we can connect these, and again we could draw in the line y equals x, and we could see the symmetry across that line. So the blue graph is f inverse, and the red graph is f. So normally we're not going to have a set of ordered pairs or a graph given. Normally we're going to have a formula for the function given. So soon we want to talk about how do we find the formula. First we'll list some properties here that we've kind of listed other places, but the domain of f should be the range of f inverse. The range of f should be the domain of f inverse. When we compose a function and its inverse, we should get back to where we started because one undoes the other. So if I take an input x, I put it into f inverse, and then I put it into f, I should come back to where I started, and that's x. We want to make a note that it's only good for x in the domain of the inside function. So remember, when we're composing these functions, we have to be able to get through that inverse, the first function first. So f of f inverse of x is true for the x in the domain of f inverse. F inverse of f of x equals x, but only for x in the domain of f. And then, like we had written, the graphs of f and f inverse are symmetric with respect to the line y equals x. Okay, so turning our attention to finding formulas for an inverse given the formula for f. The first step is to switch your variables x and y. So put the x where the y was, put the y where the x was, but don't change anything else. That's where you've what's called define the inverse implicitly. And then what you try to do is solve for y in terms of x, because we always want to solve for our output, and then switch to your inverse notation. And then if you want to, you can check that the composition of f and f inverse gives you x. I'll try to remember to do that at least once. So let's see, if I want to find the inverse of this particular function, f of x equals 2x minus 3 over x plus 2. My original f, I'm going to write with x's and y's for a minute. That would be y equals 2x minus 3 over x plus 2. I'm going to make a note that the domain of f is pretty easy to see. X can't be negative 2. But the range of f would not be easy to see without a graph. So what we're going to do is wait till we have a formula for f inverse, and that will be the domain of f inverse. So once we have the formula for f inverse, we'll be able to come back and write down what the range of f would be. So my original function f would be y equals 2x minus 3 over x plus 2. I'm going to then write down the implicit inverse, which is where I switch x and y. So I'd have x equals 2y minus 3 over y plus 2. And I want to solve for y if I can, because I want to solve for my outputs. And when we say solve for y, that means we need to get a single y on one side and everything else on the other side. The other side of the equation should not involve y at all. So first I would want to clear the fraction by multiplying on both sides by y plus 2. And I'll distribute. And then this step is where it can get confusing about what to do. We want to add or subtract to get all terms involving y on one side and everything else on the other. So I want to move the 2y over, so I would want to subtract. So I'd have xy minus 2y, and then I want to move the 2x out of the way because that doesn't have a y in it, so I would subtract 2x. So I'd have negative 3 minus 2x on the other side. The reason I want to add and subtract to get all the y terms on one side is so that I can then factor out the y. And that's the key to getting y all by itself on one side. So now I can factor that y out, and I have y times the quantity x minus 2 equals negative 3 minus 2x. And then I'm able to divide both sides by x minus 2. And that's the explicit inverse, which is what I want to get to. And once I'm there, then I can switch to inverse function notation. So I've figured out that f inverse of x is going to be negative 3 minus 2x over x minus 2. If you want to, it's fine to factor the negative out and then even take a negative out of the denominator. That would be the same thing. And you could cancel those negatives. You could have 2x plus 3 over 2 minus x. That might look a little nicer, but the original that we had is just fine as well. But it's easy to see the domain of f inverse here. We can't have a 0 in the denominator, so x can't be 2. And then again, the range of this f inverse, not so easy to tell without a graph, but it's the same as the domain of f. So I can go back now and fill in the range of f would be y can't be 2 from the domain of f inverse, and the range of f inverse would be that y can't be negative 2 because that was the domain of f. So x and y reverse spots. So let's check at least one of these, whether f of f inverse of x gives us x back. And this is optional. But good practice with composition. So f of f inverse would be f of 2x plus 3 over 2 minus x. So we use the structure for f and put this input where each x was. So that's going to be 2 times this group minus 3 over this group plus 2. It's a mess, but it's a complex fraction we can clear up. So I would multiply it all by 2 minus x over 2 minus x to clear up that complex fraction. So we'll have 2 times 2x plus 3. In that first group, the 2 minus x factors would cancel. Minus 3 times the group 2 minus x would be my new numerator. And in the denominator, I have 2x plus 3 plus 2 times the quantity 2 minus x. So let's see what we get. We get 4x minus 6 plus 3x in the numerator if I expand and distribute. And in the denominator, I have 2x plus 3 plus 4 minus 2x. And that gives me x over 1, which is just x, which is what I wanted. So again, the check is optional, but it's nice to see that the function and its inverse return x the way they're supposed to. We could look at the graphs to see that they're symmetric across a line y equals x, but I think we'll just move on to the next example. I tried to choose examples that are a little more complicated than some of those we did in intermediate algebra. So in that one, just the fractions made it a little more complicated. Here, the idea of restricting domains is going to make it a little more complicated. So in example 6, we want to find the inverse of f of x equals square root of x minus 4. So we'll start the same way. Our original f is y equals square root of x minus 4. The domain for that function would be x minus 4 greater than or equal to 0. So the domain of f would be, looks like 4 to infinity, or x is greater than or equal to 4, whichever way you want to write that. The range of f, this isn't that bad. We can figure out the range just fine. This is just a square root graph shifted 4 units right. So the range should be y greater than or equal to 0. So we should be able to write down, even before we have a formula, the domain for f inverse needs to be x greater than or equal to 0, because that's the range of f. And the range for f inverse is going to have to be y greater than or equal to 4, because that's the domain of f. Again, we have x for the domain of each one, so the variable names are different, but the intervals should be matching. So the domain of f, 4 to infinity, the range of f, 4 to infinity. So there's our original function. Then we have our implicit inverse, where we switch x and y. So x equals square root of y minus 4. That is telling us the relationship that will be true between the inputs and the outputs, but we want to solve for the output. So solve for y. So to solve for y, we can square both sides to undo the radical, and then add 4 to both sides. And I wrote them in the opposite order, but y equals x squared plus 4. But we know that that graph is the graph of a parabola. So this is not one-to-one. We need to restrict the domain. And to do that, we look back to the range of f. That was y greater than or equal to 0. So our restricted domain needs to be x greater than or equal to 0 only. So f inverse would be not just x squared plus 4, but x squared plus 4 with the restriction that x is greater than or equal to 0. And then if I sketch that on the same graph as this, I can see that I have that relationship that the graphs are symmetric. So this is f inverse, this is f. And they're symmetric with respect to the line y equals x. So you want to be always paying attention to the domain and range of the original and the final, so that you know whether you need to restrict the domains in any way. So again, answering f inverse of x equals x squared plus 4 would not be correct. You also need the restriction x greater than or equal to 0 to get the correct one-to-one function for the inverse for the given function. Example 7 is similar, except that we're starting with the parabola and then working our way toward the square root function. It's a little more complicated. So consider this function, f of x equals x squared plus 3x. Let's think about the graph of f. So the vertex would be opposite of b over 2a, so negative 3/2. You know, I'm going to change this so it's not quite as ugly as that. Let's change it to 4x. So let's do f of x equals x squared plus 4x instead. So the vertex would be x equals opposite of b over 2a, so negative 4 over 2, so negative 2. And then y is f of negative 2, which would be 4 minus 8, so negative 4. We know the vertex is a key point to know when we want to restrict the domain, because that's where it turns around and everything falls apart in terms of the one-to-one properties of the graph. We can also see that 0, 0 would be on this graph, and negative 4, 0, if we look at the factored form. So we have a decent picture of the graph. We know it goes through this point, negative 2, negative 4, and it would open to the right, or open upward, so we'd have a branch to the right and a branch to the left. We can restrict the domain however we want to keep it one-to-one, but let's keep it as large as possible. And just because it's a little bit messier, I want to do the left side. So I'm going to use this branch only. So let's do this. Let's take f of x equals x squared plus 4x and use x less than or equal to negative 2, so the left side of the graph. So the domain for f is x less than or equal to negative 2. The range for f, we can see from the vertex, would be y greater than or equal to negative 4. Now we're asked to find the inverse function. So original is f of, or let's write it as y, x squared plus 4x. The implicit inverse is x equals y squared plus 4y. And what I need to do here is complete the square. to solve for y. So if I'm going to complete the square, I want to have x equals, actually, leave some space here. Yeah, we'll do that. X equals y squared plus 4y. I want to take half of the b, the linear coefficient, and square it. I'm going to add and subtract that quantity. So that really what I'm doing is adding 0. So b squared over 2, in this case that's 2 squared, because I'd have 4 over 2 squared, so that's 4. So I want to add 4 and subtract 4. So now I've got x equals y plus 2 squared from this trinomial group minus 4. And now I'll be able to solve for y. So I'll have y plus 2 squared equals x plus 4, which means y would be either positive or negative square root of x plus 4 minus 2. I know that I want the domain for f inverse to be the same as the range of f, so x greater than or equal to negative 4. And I also know that I want the range of f inverse to be the same as the domain of f, which was x less than or equal to negative 2, so we want y less than or equal to negative 2. So we want to take the negative square root, because we want values that are less than negative 2. We want negative 2 minus the square root of x plus 4. So here is our explicit inverse. We've solved for y, and what we get then is f inverse of x would be negative square root of x plus 4 minus 2. So we use the domain of f to tell us what the range of f inverse should be, so that we could choose correctly on that square root whether we wanted the positive or negative side. If we had restricted the domain to be the right side of that parabola instead, then we would have chosen the positive square root for the square root of x plus 4 rather than the negative square root. Finally, it's asking us to sketch f and f inverse on the same set of axes. We already have a sketch of f above there. Let's see, we have negative 2, negative 4 for its vertex. So f is like this. And then f inverse, we can just say, well, we've got the square root graph shifted 4 to the left and reflected and then shifted 2 down, or we can just switch these coordinates. We would have negative 4, negative 2, negative 4, negative 2, and then 0, negative 4. So something like that. And again, we can see that the function and its inverse are symmetric across that line y equals x. So this one is f inverse, this one is f. We could also, just for good measure, check that f of f inverse of x gives us x, and this won't be as messy as the other one. This would be f, we want to know, is that true? F of negative square root of x plus 4 minus 2. What is that going to give us? And that gives us, actually this is pretty messy, but we started, so we might as well finish. That group squared plus 4 times that group. So when I square this group, I have to square the binomial, which means I square the first term. The negative will square to be positive. The square root will square to give me just x plus 4. Then I have plus 2 times the product of these two terms. So that would be 2 times 2 square root of x plus 4. And then I would have plus the square of that negative 2, so plus 4. And then I would distribute this 4, so minus 4 times the square root of x plus 4. And it looks like we're close. Somewhere I have a negative sign wrong. Where is it? Because I have x plus 8, right? Let me pause here and see if I can find my mistake. I found it. I put the wrong input in right here. So right there I should have plus, no, minus 2 also. So I need that included. And then that means I have negative 4 times the square root of x plus 4 minus 8. So we have x plus 8 minus 8, and then we get x the way we should. So it does work out. Our inverse was okay. It was just that I substituted the wrong input when I did the composition on that second term. Okay. One more here involving an absolute value function. So if f of x is absolute value of x plus 2, think about what that looks like. That would be our absolute value graph shifted 2 to the left. So the vertex, or the place where it turns around, is at negative 2, 0. Remember that absolute value of x plus 2 we can write as a piecewise function. On one side, when x is bigger than negative 2, or bigger than or equal to negative 2 even, we just get x plus 2. It's the same graph. But when x is less than negative 2, we can see this has a negative slope, and it has a y-intercept of negative 2 if it were to continue. That would be the same as the opposite of x plus 2. So that's if x is less than 2. So this time, let's restrict the domain so that it's just the right side of the graph instead. So we're just using this branch, since we chose the left branch of the parabola. So here we'll take f of x equals absolute value of x plus 2, but just x greater than or equal to negative 2. And because of this, we can use the same thing. F of x equals, instead of the absolute values, just x plus 2. Because on the interval for x greater than or equal to negative 2, absolute value of x plus 2 is the same as x plus 2. So it's fine to just use x plus 2. If we had chosen the left branch, we would have used negative times the quantity x plus 2, or the opposite of the quantity x plus 2, and the restriction that x would be less than or equal to negative 2. So find the inverse function. First, let's say the domain of f is x greater than or equal to negative 2, as we stated. The range of f, we can see from the graph, is y greater than or equal to 0. So for the inverse, we want the domain to be x greater than or equal to 0, and the range to be y greater than or equal to negative 2. So let's find it. So our original is y equals x plus 2 with x greater than or equal to negative 2. Our implicit inverse would be x equals y plus 2, and we can write y greater than or equal to negative 2. solve for y. This one's pretty easy. Y equals then x minus 2. We don't need to write this about y, but it doesn't hurt. So our explicit inverse is that. So we can switch to inverse notation. F inverse of x is just x minus 2. But we do need the restriction from the domain that x is greater than or equal to 0. So we don't want to write the restriction about y, we want to write the restriction about x, and that comes from the range of the original function. So we don't want the entire function x minus 2, we just want the part that would be the inverse for the given graph. So f of x was x plus 2, just for x greater than negative 2 or equal to negative 2. And f of x is, f inverse of x is x minus 2. And that's just for x greater than or equal to 0. But you can see again, these two are symmetric across that line, y equals x, the way we want them to be. Lastly, we have an example here that's just an application of these inverse functions. We've got the function t of g equals 1565 plus 0.15 times g minus 15650. It happens to represent the 2007 federal income tax in dollars for a married filing jointly filer if the modified adjusted gross income is g dollars, where g is somewhere between 15,650 and 63,700. So the inputs for t are the gross income, which they've labeled g, and the outputs are the tax, and they've labeled that t. So the domain of a function g is, or function t is g between 15,650 and 63,700, or let's just write it as this interval. And then the range of t we can come back to later. Actually, let's just get that now. So it would be whatever the t value is at 15,650. Let's get a calculator here. So 1565 plus 0.15 times x minus 15,650. I'm going to do a table. And I want to put in, I'm going to do table sets so I can enter values that I want to. I want to put in 15,650 for G. I can see that if I had been paying attention, I would just get that second factor to cancel, so I should just get 1565, which we do. And then if I put in the other endpoint, if I put in 63,700, we get $8,772.50, 8772.5. So the range for this function t is 1565 to 8772.5. And those are tax values. So the income range is our domain, and the output range, those tax values, are our range for the function. So given that the tax due is an increasing linear function of modified adjusted gross income tax, find the range of the function t. Well, we just did that. The idea is it's increasing and linear. So at one endpoint, we're going to have the low value for the range. At the other endpoint, we're going to have the high value for the range. So we'll rewrite it, but we already did that step. And then they're asking us to find the adjusted gross income as a function of the federal income tax and talk about the domain and range of that function. So here we want our input to be t and our output to be the g values. So we want to take the relationship we had, t equals 1565 plus 0.15 times 15650 minus g, and solve for g. So they're just asking us to reverse the relationship, right? Or find the relationship in the other order. So t minus 1565 would be 0.15 times 15650 minus g. So if I divide by 0.15, and then maybe subtract 15650, or I'll do this the other way. I'll add g to both sides and subtract this fraction. So I could write it that way, or I could figure out what 1565 divided by 0.15 is. It's a little bit ugly. I'll just leave it in this form. So here is a function that gives us the gross income as a function of t. So if you know how much tax was paid, we could figure out the gross income. The domain here would be the set of t values from above. So t between 1565 and 8772.5. The range from the other one, and then the range here would be the set of g values, and that would be the domain from the other one that was given as 15650 to 63700. And we could just take a look at those graphs and make sure that they're symmetric across the line y equals x. So we already have the first one entered. Now I'll do 15650 minus x minus 1565. That quantity divided by 0.15. And I'll change the window so that it's, I'll do, I don't know, 0 to 70,000 for both. So that'd we can see everything we need to see, I think. Making my X scale rather large so that we can see. I'm going to do a zoom square so we can see that, and then I'm also going to do the line y equals x so we can check for that symmetry. It's hard to tell for sure, I think, in that window. Let me pause this again and make sure that I don't see any errors anywhere. I did find my error. It was right here. I subtracted in the wrong order. I miscopied that. So I'm glad we checked that graph because it didn't look symmetric the way I wanted it to. So I should have had g minus 15,650 instead here. So we want to add 15,650 to that instead. So then let's take another look at those graphs. That minus should be a plus. Now the graphs look symmetric across the line y equals x like we want them to. So again, it's good to have multiple ways to look at this so that we can have a check. So we can either check the graph for symmetry, or we can check a composition too and see if the composition gives us back the input the way we want it to.